Hello, we have had 4 weeks of discussion of macromolecular systems in their introduction, which is largely focused on the macromolecular nature and structure. And this week and next couple of weeks are going to be focused on properties. And we will look at mechanical, electrical, and physicochemical properties of systems. Uh, One of the main ways in which properties can be changed is by changing the macromolecular nature itself. And molar mass, as we have seen, is a very important criterion for determining the overall performance of macromolecule. We also saw that the molecular architecture plays a very important role, and cross-linking is one of the ways in which a fair number of polymeric products are made appropriate for a given application. And so, for example, any sealant application, any gasket application, if you see, it's a material which is going to be cross-linked material. Similarly, for electrical insulation, polyethylene we think of as a grocery bag material, but for high voltage electrical insulation, it's cross-linked polyethylene, which has the right amount of hydrophobicity because of only CH2, CH2, CH2 everywhere. But cross-linking gives it the required stability for long-term electrical performance also as a very good insulator, which does not fail easily. So cross-linked polyethylene, for example, becomes a product which is in a completely different domain, a very important application. So in general, cross-linking is induced in a material to improve its performance and improve its stability. But the flip side of it is also recycling or reshaping of these is not possible because of the cross-links. As we will see, cross-links basically imply the molecular weight of the overall sample is infinite. The whole big tire, for example, is one giant macromolecule. And but without the crosslinks, a tire cannot really function. And so therefore, these materials have very superior properties. At the same time, they're challenging in terms of their overall sustainability. So in this lecture, I want to highlight this sustainability aspect by also looking at how is cross-linking done in biological world. So with biomacromolecules, what is the type of cross-linking that is there? So we look at cross-linking and engineering materials first, and then close the lecture by looking at biomacromolecules. So we'll look at what is meant by cross-linking and some examples where we look at both synthetic applications as well as biomacromolecular systems. So the cross-linking is one could pose a question as to, macromolecule is already a very giant molecule. We have repeating units, which is 10 to the power 4 or even a higher number of repeating units. What's the need for even more increase in the molecular weight? Because as I mentioned, once you have cross-linking, basically one macromolecule is joined with all the others, and basically, so you have an infinite molecular weight. And so I can start from one end of the macromolecule and I can travel basically all the way. And so it's like a maze where one end of the sample is connected with another end of the sample by just traveling along macromolecular chains. And so, of course, cross-linking is done because stability is much higher, whether it's thermal stability, whether it's mechanical stability. The resistance to solvent or whatever other physicochemical environment that the material sees, important from the point of view of, let's say, acid solutions it is being exposed to, or oil it is being exposed to. So quite often the materials with crosslinks end up showing better performance. Now, can you imagine why would solvent resistance of such a crosslink polymer would be better then compared to if, let's say, these macromolecules were just randomly organized, as in case of either a branched or a linear polymer? What does these crosslinks, which are chemical crosslinks, what do these crosslinks do in terms of both mechanical stability as well as solvent resistance? And these covalent bonds are of course permanent bonds, as opposed to the interaction points here, which are based on physical interactions and entanglements. So what is it that is related to cross-linking that makes it so rewarding in terms of performance? The other thing that you can also consider is because of these cross-links, the elasticity behavior is generally ensured. So if we think in terms of stress strain curve, as we have seen in the 30-second lecture, that for a heavily cross-linked polymer, we basically have a brittle failure, but you have an elastic behavior when we look at sigma stress as a function of strain. So if you want perfect elastic behavior, then cross-linking induces that. So because we have cross-link points which are permanent, the macromolecular orientation and other phenomena associated with yield and plasticity are not present at all. So sample will extend just based on energy, because the macromolecules will get displaced with respect to each other, but beyond a certain point the chains will break and then will be a failure of the sample. So we have basically induced more elasticity in the sample if we introduce a cross-link point. The same thing is true in the rubbery state also. Because these cross-links, if we have a rubber material which is a lightly cross-linked system, polymer chains are dangling between cross-linking points. And so one cross-link point and another cross-link point, and when we stretch, the segment can stretch itself. And that's again the origin of rubber elasticity and any of the polymeric material in its rubbery state. So therefore, cross-linking is very important from the point of view of stability and inducing elasticity in the material. And there are several ways in which we can do cross-linking. We can distinguish cross-linking based on whether it's based on physical interactions. Hydrogen bonding can be an important source of cross-linking if hydrogen bonding between macromolecules is possible. In fact, cellulose has a very extensive hydrogen bonding network between different macromolecules of cellulose. Chemical crosslinks is what is used in many of the synthetic polymeric applications, whether it's thermoset materials or whether it's rubbery materials. We could have the cross-linking type depending on the functionality. And in this case, it depends on the functionality, as we have discussed earlier, is how many times a molecule can react. And if a cross-linker can react 4 times, then it will attach to macromolecules. And so therefore, this will lead to a different topology or structure of the network compared to a trifunctional. So depending on the functionality, we will get different types of networks and therefore different type of cross-link polymer. In terms of the backbone itself, what is the mechanism by which cross-linker and the backbone or the macromolecule interact? So what is the nature of these linkages, cross-link, which are being formed? So for example, in case of diene rubbers, we have the double bonds associated with the backbone itself. And these double bonds can be used for vulcanization. In case of non-diene rubbers, such are not present, but then free radical has to be formed using peroxides or other initiators and cross-linkers so that cross-linking can happen. So depending on the mechanism of cross-linking reaction, we can distinguish the cross-linking type. We could also distinguish cross-linking based on what is the stimulus for cross-linking. So for example, is acidic environment there, or is temperature, high temperature is required before radicals can get generated, or in the presence of UV light or other light based radiation, can we have enhanced cross-linking, or cross-linking can be initiated based on these. So therefore, these are various ways in which cross-linking is induced into the materials. And just to look at this question, clearly since I'm discussing it on this slide, diacumyl peroxide is a cross-linking agent, but you can think of which of these classification does it belong to. Is it a physical or chemical cross-link that diacumyl peroxide will form? Is it a trifunctional, tetrafunctional, difunctional? What kind of cross-linker is it? What is the backbone requirement if diacumyl peroxide is being used as a cross-linker? And then what is the stimulus required? Does diacumyl peroxide perform when UV radiation is there, or does it perform when pH is right, or does it perform when temperature is high? So all these aspects can then distinguish as to dicumyl peroxide is a cross-linking agent and how effective it is for cross-linking different types of polymers. So let's look at the covalent cross-linking and one example of it. And so here, for example, we can look at an epoxide and an amine reaction. And so this is the epoxide linkage, and this can react with amine. So I have not drawn here the other parts of the chain segment, but basically you can have this amine attached to several. There are tetraamines and triamines, and where the group also can be hexa group C6, or it can be different groups. There can be branching also. So all of these possibilities are there, but basic reaction is between epoxide group and amine for epoxies. And when this reaction happens, what you have is basically the one more bond is formed where NH, and so this hydrogen from the amine group basically forms the hydroxyl group. So this is the reaction. So from epoxide we go to this epoxy molecule, but what you can notice is there is NH still remaining. So now another epoxide can come here. So you can draw another epoxide, and this can react with this NH. And so if I have a tetraamine, 4 such reactions are possible. And so that's how the cross-linking happens, and the molecular network keeps on building. So if I look at different stages of what's happening during a cross-linking reaction, initially at low time, basically I will have only these fragments, which are smaller molecules. So in a sample, I'll mostly have these small molecules. If I go to slightly later stage, now what is happening is there is some amount of cross-linking, but there is some amount of small molecules also present. When we go to a critical point called the gel point, what happens is all throughout the sample, now there is a percolating network. And there are, of course, smaller molecules also present. So as cross-linking happens, you would expect viscosity to increase because molar mass is increasing. And we will discuss this when we look at the rheological response of polymeric system. But we've already discussed the mechanical properties of the polymer. In the 32 lecture, for example, we looked at stress strain response. And generally, we will not look at stress strain response for a liquid material because they can keep on deforming infinitely. We know that liquids cannot withstand any stress. But if this three-dimensional network is formed, then it can withstand. And so that is the point at which, in fact, modulus start to be non-zero. And so we can measure the modulus, even though there are some smaller fragments present in the sample, since there is a percolating network. And as I mentioned, from one point of the sample, you can go basically to the other end of the sample, traveling along the macromolecules. And so that's called the gelation point. So this transition is called sol to gel, from a solution liquid-like system to a gel solid-like system. And this gel point is also very important from a practical point of view, because all the shaping has to be done before this gel point is reached. Because once the gel is formed, it acquires a solid-like feature. So if you were to do this in a beaker, and if I were to just take the sample initially and do a stirring, what I'll get is a liquid-like response where it will stir like a liquid. But at this point, when I stir, it will rotate like a solid. It will become one block. And even though it's a soft solid, because there are many small molecules still present, some of the pre-polymer is still there, some of the hardener is still there, small molecules, but the gel fraction is spanning the whole sample. And so therefore, it will rotate like a big solid blob inside the beaker, and there will be slip between the overall blob and the surface of the beaker. So therefore, this is one way to also monitor cross-linking reactions. We can measure either the viscosity or the modulus and try to monitor what is the way the extent of cross-linking is there in the sample. And so the sol-gel transition is a very important indicator of when to do what kind of processing when we are dealing either with thermoset materials or with crosslink rubber materials. And because of this crosslink, once formed and once we get a three-dimensional network, we have seen that recycling is a challenging aspect, because we have to first think in terms of decrosslinking so that we get rid of the three-dimensional network, because tire, for example, is one giant molecule. So recycling of tires, for example, therefore is quite challenging. We can't melt it because it's not macromolecular in terms of linear and branched. It's one giant macromolecule connected from one end to the other. So if we could decrosslink it, then we could reprocess it. And of course, if we have to get it into raw materials and then make it part of the overall cycle, then we need to also depolymerize it. So in case of recycling of thermoset and crosslink rubber polymers, there are additional challenges when we compare them with other linear and branch polymers. So the question that can be asked is, can we not have a set of crosslinks which are maybe more amenable to manipulation, and decrosslinking may be something which is achievable? And so there are several examples of crosslink systems which are there. And from an engineering point of view, of course, what we have used are covalent systems, where, like we saw in case of epoxy, there is a specific covalent bond formed by the crosslinker. And that's why crosslinker are also called hardeners, because they basically induce from a pre-polymer liquid-like material to a final thermoset gel solid-like polymer. It hardens the material. And the other applications of covalent crosslinks are also in there in superabsorbent polymers and various other applications of drug delivery, where the solvent is present along with the crosslink polymer network. So these are what are challenging from the recycling point of view. But can we not think of crosslinks as physical crosslinks? In which case, decrosslinking as a process may be easier to achieve. At this point, I would like you to just think about it as to why cellulose is so stable. Because cellulose does not have chemical crosslinks. So though I'm trying to point out that chemical crosslinks are the ones which are more difficult to decrosslink, sometimes even secondary crosslinks such as formed by hydrogen bonding networks in cellulose can also be difficult. We will also see another example of chitin as a polymer. So many of these systems, physical crosslinks can also be challenging. But in general, we will find physical crosslinks to be easier to decrosslink, because, for example, crosslinks can be formed by just hard segments in a sea of soft segments. So the black chains here are basically soft, and they are distributed in this hard. So this hard point, wherever, for example, polyethylene, polypropylene. So wherever red polypropylene chains are there, they are surrounded by black polyethylene flexible chains, and the red part of polypropylene chains will try to act as a crosslink point, keeping together fixed the polyethylene chains which are more flexible. We could also have, as I mentioned, hydrogen bonding or maybe hydrophobic interactions as the specific sticking points between different macromolecules and inducing physical crosslinks. Crystals could also form a crosslink. So if we have flexible chains in the rubbery state, but there is crystalline portions, then what happens is we know that each and every lamella will have chains sticking out of it. So basically different chains, flexible chains, are bonded together through this crystalline portion. So crystalline portion can also act as a cross-linking point. And the way we can decrosslink this is just to melt it. So once if the crystal is molten, either by increasing the temperature or by adding a small molecule which will change the crystallization condition, so crystals can be taken away. And in that case, then decrosslinking can happen easily. There's also an interesting possibility which has been discussed a lot in research literature in the last 10-15 years, is related to supramolecular polymer. The concept here is to get away from covalent bonding even in macromolecular formation, because I talked about in the previous slide about de-crosslinking and depolymerization. So both are challenging aspects from a sustainability point of view. Now, can we not assemble a polymer and which is called a supramolecular polymer? So here the monomers are also attached to each other through physical interactions. And of course, many of these materials are nowhere near the applications that we have, for example, from an epoxy material or even polyester material. But this is an interesting possibility that we can assemble and disassemble as we want. And so some of these materials can probably give partial answers to overall sustainability challenges which we are facing. So just to again highlight as to how is cross-linking done in natural world and in biomacromolecules, we'll just take a close look at pectin calcium system. And as we have seen earlier, pectin is a fairly complicated molecule with different types of hydrophilic, hydrophobic domains and branches being present. But one of the key things that's there on the pectin molecule is the carboxylic acid group. And this can be cross-linked using a calcium ion. And so the importance of calcium in overall biology is well known. And one of the functions that calcium also does is cross-link with pectin. Now, why is this important? Because in plant cell wall, for example, we have distribution of pectin, cellulose and hemicellulose. And it's the pectin with its cross-link with calcium which determines how the cell wall behaves. In fact, when a fruit ripens, we know that its skin becomes soft. And part of the processes which happen to change the mechanical response of the skin is what happens to pectin. If, let's say, instead of carboxylic acid groups, we have this group, then it can't be cross-linked using calcium. So the way the calcium cross-links are present in pectin and the nature of amount of cross-linking which is present is very important determinant of what the plant cell wall property will be. And this is not all of it. How calcium cross-links pectin is also extremely interesting. So we can have basically one pectin chain and another pectin chain being cross-linked by this calcium. So calcium can, I'll just draw it using this red highlight. So basically we have this calcium interacting with two COOH groups from two different chains. So there is a COH group here and there is a COH group here. And this is the cross-link which is formed. So this is one way of doing the cross-link. But what happens based on the COH which are located on the pectin chain is a very interesting formation which is like this, where there is a pectin chain and then there is calcium . And I don't know if you can think of what this reminds you of. This is called an egg box cross-link. It is as if calcium is sitting in the slots formed by the pectin box. And moreover, the fascinating aspect of macromolecular assembly is that we can have stacking of such egg boxes on top of each other. So we can have stack of egg boxes. So look at how cross-linking variety is there. Different types of cross-links, different amounts of cross-link by manipulating the chemistry of the macromolecule, and the molecular architecture with hydrophobic, hydrophilic, different groups to again ensure different types of interactions. So a biomacromolecular system such as pectin has all these varieties from basic monomer level all the way till cross-linking to do tunability of its properties. And so this can serve as an inspiration for us to also think of polymeric products with such tunability, but as sustainable as these pectin chains are, because once the fruit is done, the peel can easily get recycled and become part of the overall cyclic processes. So can that be done with the polymeric materials that we have? And just to see these multiple heterogeneities and complex assemblies of biomacromolecules that we have, you could also just look at collagen and its cross-linking. Collagen is a basic component of tissues, and it's a very important structural component. It gives mechanical properties, barrier properties, and it's basically what makes it possible for tissues to sustain themselves. So what kind of cross-linking is there in collagen? Or actin, which is again part of cell wall and the cytoplasm. And so how cross-linking in these kind of systems also is very influential in determining the overall performance, and quite often the elasticity is induced based on these cross-linking networks. So generally network polymers and their cross-linking is very important area for us to look at because of the practical engineering applications as well as from the point of view of understanding biology. Now, can we merge the two in terms of getting the right amount of cross-links for the engineering application where decross-linking can also be easily achieved? So with this thought, we will close this lecture. And the peroxides are actually very common materials for initiating and cross-linking reactions. So they are basically free radical processes by which they do the initiation and cross-linking in the monomer or the macromolecular as the need be. Thank you.